Hello, and we're going to be going through 9 of the questions that we assigned in Chapter 4. So the first question says, suppose that the acceleration of an object is 0. Does that mean that there are no forces acting on it? The answer is no, because just me standing on the ground right now talking to you, there are gravity's forcing me straight down, and there's a supporting force provided by the floor that's lifting me straight up. So just any regular old person standing on the ground, there's gravity and there's a supporting force. So no. The next question, number 47, it says a rock is dropped from a bridge into a valley, and it's falling down. According to Newton's third law, the rock must also be pulling on the earth, yet the earth does not seem to accelerate. Is this true? Oh, absolutely, it's true. The earth pulls down with the force of gravity on the rock, and the rock pulls up on the earth with that same force of gravity. But the thing is, this force, let's just give it a number, like 10 newtons, for instance. The mass of the rock, maybe it's 1 kilogram, and you can find the acceleration roughly 9.8. But you do that same calculation down here, that 10 newtons, but the mass of the earth is gargantuan. It's like 10 to the 23rd or something like that. And then you find the acceleration. It's very, very small. So the acceleration is very, very tiny. The next one, number 60, it says Joyce and Afua are skating, and Joyce pushes Afua. So let's see. They're skating, and she gets pushed with a force of 5 newtons. This young lady has a mass of 40 kilograms, so when you take 40 times 9.8, you get 392. That's her weight. I'm assuming that she's probably on level ground, so the normal force is going to be equal to 392. What's her resulting acceleration? So then what I'm going to do is I'm going to plug it into this equation, F equals ma. And remember, it's always the net force, because these two forces cancel each other out. So my net force is 5 newtons. Her mass is 40.0 kilograms, and the resulting acceleration would be 5 divided by 40. And it comes out to be 0.125, or the acceleration is 0.13 meters per second squared. The fourth question we have in our set is number 61. There's a car of mass 2,300 kilograms. So this thing has a weight of 2,300 times 9.8. And that equals 22,540, or 23,000. Again, I'm assuming it's probably on level ground. So, oh boy. So the normal force comes out to be the same thing. And it's slowing down, so there's some braking force. Again, there is nothing pulling it forward. There is no engine force. That's a common misconception with this problem right here. So what we're going to do is we're going to use F equals ma. And again, it's always the net force because these guys are canceling. So my net force is the braking force. The mass of this thing is 2,300, and the acceleration is 3. So I take 2,300 times 3, and I get 6,900. So that braking force is 6,900 newtons. Like that. The next question is 64. Your new motorcycle weighs, what is its mass? So again, this is F equals ma. So its weight, that's a newton, that's a force, so 2450. What's its mass? But the acceleration on planet Earth is 9.80. So you take 2450 divided by 9.8, and you get 250 kilograms. So I probably I have to have three significant figures, so I'm probably going to have to do it like this: 2.50 times 10 to the third kilograms as my mass. The next question, 68. There you have a dragster starting from rest. And this thing has it's 873 kilograms. So it's got a mass of 8560. Oh, weight, I mean. And I'm sure that the engine is providing some force. Let's see. It says letter A, find the average acceleration. So I know that its initial velocity is 0, that its final velocity is 26.3. I know that the time is 0.59 seconds, and I'm looking for the acceleration. So I could probably just use this equation right here. Final velocity 26.3, initial velocity 0, acceleration, that's what I'm looking for, and the time is 0.59. So my acceleration is 26.3 divided by 0.59, and that comes out to 44.6. So this is my first answer for part A. Part B, what is the magnitude of the average net force? So I'm going to take that right into this equation right here, F equals ma, because that's the net force. And remember that these are canceling, so they're not part of the net force. So my net force, actually, my mass, which was 873, times that acceleration of 44.6. And it comes out to be 338,900. This is part B. So part C says, assume that the driver has a mass of 68 kilograms. What is the horizontal force that the seat exerts on the driver? So he is 68 kilograms, is that right? Okay. So again, I'm going to plug her into F equals ma. So he has a mass of 68 kilograms, and he's doing that same acceleration of 44.6. So 68 times 44.6. And that comes out to be 3,000, is he 68.0? 68. So 3,000 newtons, or 3.0 times 10 to the third newtons. Part C. The next question, number 73. It says a 65 kilogram diver jumps off a 10-meter tower. So let's make a little picture here. I know that this is 10 meters. Find the diver's velocity when he hits the water. So I know that my initial velocity of this diver, since he just jumps off, is 0. I know the acceleration, because he's under the pull of gravity, is 9.80. I know that the distance is 10 meters. And I want to know his velocity. So the equation that doesn't use time is this one. So I just plug everything in. VF squared, my initial, that's always nice when it's 0. So 2 times 9.80 times 10. So that's going to be 2 times 9.8 is 19.6 times 10 is 196 equals VF squared. So my final velocity is equal to the square root of 196, which is 14. So I think I can go one more significant figure, because this has 10.0. So yeah, so 14.0 meters per second. That's part A. Part B says the diver comes to a stop 2 meters below. So he comes to rest down here, 2 meters below the surface. So there's an upward force acting on him. So this diver, so here he is. There's gravity pulling him down, but then there's some, I guess you call it fluid friction, fluid resistance, that slows him down, that it's like air resistance. Anytime you try to travel through a fluid like liquid or gas, you're always having to move it out of the way. So there's some up thing that pulls him back. It says find the net force exerted by the water. So the only way we can do this, so we're going to use F equals ma, and it's the net force at work here. And remember, there's two forces, and they don't cancel each other out now. I think what I'm going to do in this problem is I'm going to say that up is positive, and you'll see why. Because he's accelerating, I know that he's accelerating upwards, so I like to keep that positive. So that's going to be this is going to be a positive, the up force, and I'm going to subtract off the force of gravity, and that's going to equal his mass times its acceleration. So I'm going to have find a couple of these things. First of all, I know the force of gravity, because it tells me his mass at the very beginning is 65. So I take 65 times 9.8, and that will give me his gravity of 640. So I know the force of gravity is 640. And I know that from the problem, I'm looking for the up force. I know the mass, again, is 65. And the acceleration, that's going to be tricky. The acceleration, I'm going to have to do a whole separate problem for, because I know his initial velocity when he entered the water was 14 meters per second, and I know his final velocity is 0. I know the distance that it came to rest is 2, and I also know that I'm going to make it negative because he's going down, which is going against my positive, and I'm looking for the acceleration. So again, I'm going to have to use this equation. So my final velocity is going to be 0. My initial velocity is going to be 14.0 squared plus 2 times the negative, I don't know what my acceleration, but the distance is negative 2. So I take 14 squared, 196, that was negative 196 equals negative 4a. So 196 divided negative 196 divided by negative 4 comes out to be 49. Holy cow. That's somewhere on the magnitude of 5 G's. So this becomes 49. And it's positive because he's accelerating up. So I take 65 times 49, 3185. So my up force minus 640. So I'm going to add 640 to 3185. And I get 3825. So my up force is 3,800 newtons. I guess it says what is the net force exerted by the water? So okay, yeah, there you go. There's the force exerted by the water right here. Probably the toughest problem we've seen so far because we've got multiple forces at work. And then the last one, it says you have a 90 kilogram man and a 55 kilogram man. They have a tug of war. So 90 kilogram man, 55 kilogram man, and they're having a tug of war. The 55 kilogram man accelerates at 0.025 meters per second squared. What force does the rope exert on the 90 kilogram man? So I'm going to use F equals ma over here because I know the man's mass in this case is 55 and I know his acceleration is 0.025. So 55 times 0.025 is 1.375 or 1. With sig figs, I can only have 1.4 newtons. So that's the force here that's pulling him. What force does the rope exert? The exact same force. Right there. All right, so in number 70, it says a grocery sack can withstand a maximum of 230 newtons before it rips. So what I'm going to do, I'm going to draw my grocery sack. And the biggest amount of force is 230 newtons. We know that's the biggest it can be. I know that it says that there's 15 kilograms of groceries in it. So there's 147. So right now, if I was just holding it standing still, there would be 147 newtons. And that would be good. Like if I was just holding the thing, supporting it from falling, if I put 147, that's well below its threshold of 230, and I'd be good to go. But the thing is, it says I'm accelerating it. I'm accelerating it up at 7.0 meters per second squared. So I know that my pull force is actually, it has to be bigger than gravity in order for that to accelerate up. So the way I'm going to figure it out is I'm going to use F equals ma. And remember that I use the net force. And the net force is the combination of the two forces that are at work here. So I'm going to say that up is positive. So I've got a pull force, and I'm subtracting gravity because gravity is negative. The mass of everything is 15. Oops. Maybe I'll just leave it as a bunch of variables to begin with, and I'll fill everything in. I don't know the force I'm pulling with. I know that gravity is 147, and I know that the mass is 15, and I know that the acceleration is 7. So when I take 15 times 7, I get 105. So my pull force is going to be equal to 105 plus 147. So it comes out to 252 or 250 newtons. So that's how much my pull force actually is. And that's bad. So the question asks, will it rip? No, yes, this will rip.
So remember that you're using the net force when you're doing this F equals ma. You're using the upward pull, the upward pull of u subtracting off the pull of gravity. And in this case, the pull by u is bigger because we have acceleration. Remember, you always look for acceleration. The acceleration is key to telling you which of the forces is bigger. If there's no acceleration, that means that there's no net force, that these top and bottom forces cancel each other out.